Hello everyone, thanks for following this presentation on mechanical properties and shrinkage of alkali-activated slag concrete. Today I'm presenting strength development and shrinkage results that I got for two alkali-activated slag mixes. I'm comparing them with existing models from the FIB model code. And since strength development and shrinkage are two time-related properties, I will take a look at the degree of reaction of the system through isothermal calorimetry experiments and reaction kinetics models that I developed. Alkali-activated materials are precursors, just like cement, with lower calcium oxide content replaced by aluminum and silicium oxides. And dependent on the CaO content of the precursor, one can get more or less CSH phases and more or less alumosilicates, forming an alumosilicate polymer network. In the experiments that I did, I used only one type of slag with two types of alkali-activated solutions, which are necessary to have a proper reaction. The difference between these two solutions is the molar ratio between the SiO2 and Na2O content. One solution has a pretty low SiO2 content of 0.5, and the other one a pretty high, 2.2. Depending on the property I was looking at, I worked on a paste level or on a concrete level. And the first property I looked at is the strength development of this system on a concrete level, where the geometry was cylinders of 10 centimeter diameter and 30 centimeter height. What we can see from this first graph is that the strength development of the system is pretty comparable to a normal concrete 42.5 predicted with the FIB model code. And dependent on the mix, the development is either faster or slower. For the Young modulus here on the right, we can see that for both mixes, the development is faster. The second property I looked at is the shrinkage of this system. And firstly, on a paste level with prisms of 4 by 4 by 16 centimeter cubes. I looked at both autogenous and drying shrinkage with exposure after 7 days, and two conclusions can be raised from this diagram. Firstly, increasing the SiO2 content in the activator solution increases the shrinkage. It's a difference between the orange and the blue curves. The second conclusion is that the low SiO2 mix presents low drying shrinkage. And this can be seen also on a concrete level, this time made on prisms of 10 centimeter diameter, 30 centimeter height. And the second conclusion which can be done is that alkali-activated slag presents bigger shrinkage than the one predicted by the FIB model called 2010. And as I said, to understand and model strength development and shrinkage of alkali-activated slag, one should look at the kinetic reaction and predict the degree of reaction. And to do so, one can use, for example, isothermal calorimetry experiments on a paste level. The pastes were prepared outside of the calorimeter, mixed and homogenized, and put in less than 5 minutes in the calorimeter chamber. From the calorimeter, we get these two types of curve, the heat flow and the accumulated heat release. And from there, we can get three outputs. The first one being the final accumulated heat release obtained by extrapolation of these curves on the right, with, for example, the exponential model, which is pretty well explained in the literature. The second thing we can look is the number of peaks and the type of peaks we have. And just at looking when the peaks occur, we can see that increasing the SiO2 content in the activator solution delays somehow the reaction since the curves are shifted on the right. So here the conclusion of the experiments is that different activator solutions present different type of reactions. From this experimental data, one can now try to model the reaction kinetic of alkali-activated slag with water glass. Chi and Day showed that such a system presents a three-peak behavior. The first peak being the dissolution and the wetting of slag occurring during the 31st minutes. It is not displayed here, and it's not taken into account into the modeling process. Existing models, such as the one from R2 Kilo, are adapted for cement-based systems, which show only one peak. As a consequence, they cannot be taken directly to model alkali-activated slag systems with water glass. Some authors propose to use it only to model the last peak of such systems, while others decided to cut the curve into two parts, each part being related to one of the peak. And each part is fitted with either the Knudsen model and or the exponential model. And even if they don't give insights on the mechanisms occurring behind it, they allow us to predict the degree of reaction along the time. Here, the goal is not only to predict this degree of reaction, but also to provide some possible mechanisms occurring during the activation of slag with water glass. And to do so, we use single particle models to find kinetic controlling mechanisms during this reaction. And three of them are very important: the nucleation process, modeled with an Avrami-Erofeyev function, the shrinking core process, modeled with a contraction volume model, and the diffusion process, modeled with a Ginsling-Bronstein equation. All these equations link the degree of reaction alpha tilde with its derivative along time, and the fitting is done on the reaction rate K. Usually, we do so with the global degree of reaction, for example, constructed such as this fraction, heat release divided by final heat release. And one should build this function, so the derivative of the degree of reaction in function of the degree of reaction. Nevertheless, the main hypothesis of the proposed model is not to take this global reaction degree per se, but local ones, partial ones. Actually, each the global function is decomposed into zones, each zone corresponding to one predominant mechanism. And the best succession of mechanisms which is found is first a nucleation process, followed by a shrinking core process. This is the first peak. Then you have an induction period modeled by a first order reaction, which still must be understood. And then the second peak is modeled by the classical succession of nucleation, shrinking core, and diffusion processes. In comparison to the R2 Kilo model, here we don't take as a minimum of discontinuous continuous functions. However, we take the sum of functions which can lead to discontinuities. To avoid it, sigmoidal functions are used, and they allow to have a smooth transition from one mechanism to another. After fitting in each zone and integration, one can get the cumulated heat release. And here we can see that the global fit is pretty representative of the experimental data. What we did here then is predicting the degree of reaction by putting some physical understanding of what happened in the system. From this kinetic analysis, the next step is then to study the microstructural evolution and two main aspects. First, the phase formation, which will be analyzed with chemical characterization in connection with thermodynamic modeling. and then the pore structure development. And I recall the first objective that I had. It was to model strength development and shrinkage. And this will be done further on through analytical homogenization models and pore mechanics models. Thanks for your kind attention. Please don't hesitate to ask a question. I would be very glad to answer them. See you.